So now let's talk about electromagnetic induction. The discovery of the battery was a really significant development in the 18th century. Batteries provided a continuous source of voltage, and electricity development was really able to take off. Batteries, however, are not this ultimate answer. They're expensive to make, and they don't last very long, really. Even today, battery power is much more expensive than the electricity that the power company delivers through power lines. A really cheap source of electricity would be really useful. And as soon as it was discovered that a current can create a magnetic field, physicists began to wonder if a magnetic field can create a current. And what came out of wondering about that is what we call electromagnetic induction. So let's get going. Working independently around 1831, two physicists, Michael Faraday in England and Joseph Henry in the United States, discovered electromagnetic induction. Both guys did pretty much the same thing, but here's a description of Faraday's experiment. So Faraday made a coil of wire around one side of an iron ring and connected that coil to a battery. He placed a switch in this circuit to turn the circuit on and off. And then a second coil of wire was wrapped around the other half of the ring. And he connected a second coil to an electric meter, some kind of an ammeter. Okay? When the switch was initially closed, the current flowed through the first coil and the meter would spike up, indicating there was a current also flowing in the second coil. But then the meter needle would fall back to zero, meaning that the current was no longer flowing. Electricity was somehow being induced by the magnetic field of the first coil into the second coil. The current was present in the second coil for just a really short amount of time, just less than a second. The current was it's kind of transient, and it quickly disappeared. As soon as the current built up in the first coil, the current in the other coil went away. Then, when the switch was open, the current was also produced in the second coil again, but only momentarily. So what was happening here was that when the switch was closed and the current began to flow, lines of magnetic force were built up as the magnetic field developed. The lines of flux moved outward as they were created. Henry figured that the moving lines of force cut through the second coil and induced a flow of current. Once the lines of force were in place, they no longer moved. So electricity was no longer induced in that second coil. When the switch was open, the lines of flux would collapse. They were once again moving, cutting through the second coil and inducing electricity again. It was only while there was motion between the conductor and the lines of magnetic flux that electricity was induced. The result of this then is that an EMF is induced in a conductor placed in a magnetic field, but only when there's a change in that magnetic field. Now, EMF, it stands for electromotive force, and it's simply the induced voltage when we've changed the magnetic fields in some way. Now, we can induce current in two separate ways. First, a conductor can be physically moved through a magnetic field. In that case, we can take a conductor, hook it up to an ammeter, move it through a magnetic field that's changing. As far as that conductor is concerned, it's experiencing a change in that magnetic field, and we'll get an induced current. Or the conductor can be stationary and the magnetic field can be moved. So we could have a coil of wire here and move a magnet through it, and we're going to get an induced current in that conductor. And then what Faraday did was he had a coil of wire here, and that's just like having moving a magnet through it as well, because this coil here will set up a magnetic field which induces a current in the second coil. So the production of current depends only on the relative motion between the conductor and the magnetic field. The amount of current that is induced depends on a few different factors too. One factor is how quickly the magnetic field changes. So if you move a magnet through a coil of wire faster, then it's going to produce more current. Second, the strength of the magnetic field. So you use a stronger magnet, you're going to get greater amount of current induced. And then the number of coils, that is the number of coils that you're moving that magnet through, will also determine the amount of current that's produced. Now, all that almost sounds like you're getting something for nothing, but that's not the case at all. It takes energy to push this magnet through a coil. The more loops, the more energy it takes to push the magnet through the coils. So you have to put work into the system to induce this electricity. So now remember, EMF, which is just the voltage that's induced in electromagnetic induction. Okay, EMF is induced by a change in magnetic flux rather than by a change in the magnetic field. You can think of magnetic flux as the strength of a magnetic field moving through an area of space like a loop of wire. So for a single loop of wire in a uniform magnetic field, the magnetic flux through that loop is given by this equation here, where this is a Greek letter phi, and it stands for the magnetic flux. B is the magnetic field strength, A is the area of the loop, and theta is the angle between B and a normal to the plane of the loop. Normal just being, remember, is just perpendicular. So the magnetic flux is proportional to the number of lines of force passing through the loop. The more the lines, the bigger the flux. The unit for magnetic flux is Tesla meter squared, or we sometimes use what are called Webers. So the greater the flux, the stronger the magnetic field, right? Now when the loop is perpendicular to the magnetic field, then the angle would be 0, and the magnetic flux is simply BA. When the angle is 90 degrees, then you're going to have 0 flux there, okay? So that is the basics of electromagnetic induction. In the next video, we're going to see how some of the effects of electromagnetic induction through what's called Lenz's law. We'll see you then.